bother with you. Thank you again for this class. I thank you for this time we have to study your creation. It's great that you be glorified what we do, and we all understand a little more about calculus together. You know, great pieces. Amen? So now it's probably a good time to talk just a little bit about, like, you know, the test. I don't have anything to say really about what you did on the test because I haven't graded it yet. I don't know what you did, good or bad. And probably this mic will work better if I plug it in, right? Mics are funny that way. All right. Sorry about that, guys. But anyway, if you did do, you know, poorly, or even if you just did worse than you know is your personal best, all is not lost. I do allow you to replace your final exam grade with the test 1 score if it's helpful. All right. So if you bomb this test, it doesn't mean that you can't make an A in the course anymore, right? What it means is that you need to, like, figure out what went wrong and try to adjust so that when I ask those questions again on the final, you can ace them. All right. So all is not lost. I know, you know, some of you start from, you know, further behind in terms of like where you are in terms of algebra and other things than others, and sometimes it just takes a little bit of time to get used to things. However, if things went poorly, then probably you need to devote more time to this class, right? I wouldn't say that means you need to go get tutoring. I don't really see much evidence that tutoring helps people. What I see evidence of is that people who do their own homework and ask questions about their own homework of their own work helps people. There is no other way to do calculus than to do the homework. Like, you need to do the homework. You need to do a lot of it. So that would be my advice. Not so much to seek out tutoring, but to seek out time for yourself to work on the homework. You're like, well, I work on the homework, I get stuck. So what's the point of that? Well, the point of that is, if you get stuck, you go on to the next problem and you find one that you can do. And then maybe the next class you come back and say, hey, I'm stuck on the homework problem. And then we can talk about it because we have time. We meet 5 days a week. I have time for homework questions in here. You just got to ask them, right? So don't be afraid to ask homework questions in here because you're not the only one who has those questions, all right? So now there do exist some days where I have something I need to lecture on and I don't have enough time for like everybody's homework questions, but I would say that's more often not the case in here, all right? So let me get into it. I need to start with a theorem which is a little bit formal, but it's worth it. And this is, so we're talking about differential calculus. And so we are going to soon leave limits behind and find better ways to calculate, all right? I know you guys are sad. You're like, but I like limits. Why can't we just keep doing limits? Well, no. If we had to just keep doing limits for the entirety of this course, then this course wouldn't be an undergraduate course. All right? The fact that we go past limits is part of what makes calculus, you know, arguably a freshman course. Okay, so theorem, this is Caratheodory's theorem. So Caratheodory is a famous Greek mathematician whose work is pretty deep. And Caratheodory had this alternate way of looking at differentiability. And here's how it goes. So let f be a function, all right, and a an element of the you know, of I, which is a subset of the domain. So I think this basically, another way you could say this is, suppose A is in the interior of the domain, okay, like I said on the test on one problem. Then f is differentiable at A, all right? If and only if, all right? If and only, so this IFF is an abbreviation for this biconditional symbol, all right? So if and only if. There exists function phi from I to R with the following two properties. All right, so the following two properties are, number one, phi is continuous at A, and two, it satisfies this equation, f of x minus f of A is equal to phi of x times x minus A for all x in A, in I rather. So Caratheodory said, well, you don't have to look at a difference quotient. It's enough to find a function phi that behaves in this way. All right. So let me prove this theorem for you. So the proof goes like this. So when we have a biconditional, that means biconditional means that it goes this way and it goes that way, right? There's a forward and a backwards direction. So let's do the converse direction first because it's kind of easier. Well, I'm not sure it's easier, but I'm just going to do the converse direction first. So the converse direction, so we assume phi as in theorem. All right, so I'm assuming that there exists a function which has these two properties, okay? Consider the difference quotient. The limit as x goes to A of f of x minus f of A over x minus A. How's that going to go? Well, you see, if we have this function phi with these properties, then we can replace f of x minus f of A with what? With this business right here, right? So what I have is the limit as x goes to A of phi of x times x minus A over x minus A. But that's wonderful because they cancel. And we're just lift, listen to me. Do you lift, bro? Let's see here. We're left with limit as x goes to A of phi of x. But what did we say about phi? It was what? Continuous at A. What does that mean? The function's continuous if the limit at the point is equal to the value of the function at the point, right? So this is equal to phi of A by assumption number one here. Aha! So what does this prove? Thus, f prime of A exists, and it's equal to phi of A, which is to say that the function is differentiable at A. If there exists this function phi, that suffices to give us differentiability of the function. All right. Great. So let me just say that this is equal to f prime of A, and we're done with that part of the proof. I'm going to erase this so I can go the other way. So the other direction, the forward direction of the proof, is next. All right. So now we will assume f prime of A, which of course is the limit as x goes to A of f of x minus f of A over x minus A, exists. we're going to let phi of A be equal to f prime of A. And we're going to define phi of x equal to f of x minus f of A over x minus A for x not equal to A. So we define phi case-wise. On the one hand, we define it by the difference quotient. Right, this is the difference quotient. So by the way, if you're looking for a name for phi, phi is often called the difference quotient function. You see why that is? This is the difference quotient. Phi of x is equal to the difference quotient. So it's the difference quotient function. Now, okay, I'm assuming f is differentiable. I've defined phi case-wise. It's either equal to the derivative at A, or it's equal to the difference quotient for x not equal to A. Question, does it satisfy 1 and 2? Is it continuous? Is phi continuous at A? What's the limit as x goes to A of phi of x here? It is exactly the limit of this, which we've defined to be f prime of A, which by the way is phi of A. So yes, phi is continuous at A. More than that, does it satisfy the equation in number 2 here? It does, right? If you just look at the equation that I'm going to box right here, you can take that, right? And you can do what? Algebra, and you get that. Right? So yeah, it gives us that equation. There's one special case though, which is what? When is the equation in the box not defined? X equal to A, right? What about x equals to A? So for x equals to A, notice that phi of notice that f of A minus f of A is equal to phi of A times A minus A is stupidly true, to use a technical term. Right? I mean, duh. Yeah, 0 equals 0. So we got that. So there you go. That's the theorem of Caratheodory, which basically, what the point of this is it gives us an equivalent characterization of differentiability at a point, which can be very helpful for certain proofs. Right? One of the proofs it's helpful for is one of the problems I gave you guys on your test, right? Sorry. I haven't graded it yet, so it's nothing personal. Right? Whatever happened, happened. I don't know what happened. But, so like, so check this out. Proposition, f differentiable at x equals to A implies f continuous at x equals to A. All right, so here's how that proof goes here. Since f prime of A exists for there exists phi, continuous at x equals to A with what? F of x minus f of A is equal to what? Phi of x times x minus A, right? But the truth is, that's how I defined it. It just makes the proof of the theorem nice. But actually how I think of the quotient function, the difference quotient function, is in the following sense. Almost always when I use this thing in some kind of theoretical application, it's as follows. This gives me f of x is equal to f of a plus phi of x times x minus a. That's actually kind of the more useful way to look at it. So what the Caratheodory theorem gives me is a way to look at the function in a new light in terms of its derivative in this way. Now, if I do that, check out what happens. What's the limit as x goes to a of f of x? What's that equal to? Like that, right? But you guys know limit laws. How does the limit law go here? You got yourself f of a, right? Plus the limit as x goes to a of phi of x times the limit as x goes to a of x minus a. So how's that all work out? This is what? So what's the story here? The limit of phi of x is given to us by definition of what phi is. It's f prime of a, right? By assumption. This is f prime of a. This is 0, right? Question? Okay. So that's 0. And so what we have? We've got f of a. So we have now shown that the limit of f of x as x approaches a is equal to f of a. Thus what? Thus f is continuous. If you contrast this argument that I just gave you to the one that we had before test 1, this is a much easier argument in the sense it didn't require any kind of sneaky like addition of 0 or like the argument we gave before is slightly indirect. If you use the theorem of Caratheodory, you can prove laws of differentiation through pretty much direct calculation. So like, for example, so let me just kind of tell you guys where we're going. So for the next couple lectures, we're doing a variety of things. We're either working out the derivatives of specific functions, or we're working out derivative laws. Okay? So I'm going to lead with the two basic differentiation laws because they are strongly linked to this discussion of Caratheodory. But then we'll circle back to like derive the power rule and all kinds of other things, all right? So here's a theorem that we can prove, which is that if f and g are differentiable at a, then 1, f plus g prime of a is equal to f prime of a plus g prime of a. Number 2, if we had a constant times f, then that's just a constant times the derivative. All right? But then the third one to talk about here is the product rule. F times g prime of a is equal to f prime of a times g of a plus f of a times g prime of a. So I'll just start with these three rules. These two I refer to as linearity of the derivative, and this right here is the so-called product rule. So let's see here. Let me show you the proof of 3 actually to start with here, because it's kind of the most interesting one. And so, just to get to the heart of the matter, we'll use Caratheodory. F of x is equal to f of a plus, let's call it phi sub f of x times x minus a. That's Caratheodory for the differentiability of f. But I also have that g of x is equal to g of a plus phi g of x times x minus a. That's the theorem of Caratheodory for g. All right? So I'd like to see how the product of f and g behaves. All right? So if I do that, just multiply these formulas is all I got to do. See, f of x times g of x is equal to the product of this and that, right? So if you multiply this times that, what do we get? We get f of a, g of a, plus like f of a times phi g of x times x minus a, plus phi f of x times g of a times x minus a, plus phi f of x times phi g of x times x minus a squared. So all I'm doing is just foiling out the product of those two terms. If that, can you guys see what I did there? Does that make sense? So keep in mind the theorem of Caratheodory. If we can show that there's a function which behaves as a difference quotient function for the product of the two functions, then we can use the theorem of Caratheodory to find the derivative of the product. So like, all we got to do here, guys, is notice that this is f of a, g of a, plus something, right? What we got? We've got f of a, phi g of x, plus phi f of x, times g of a, plus the product of the phi's, phi f of x, phi g of x. Pull out one of the x minus a's there, close the big bracket, factor x minus a out. All right? So then what? Let's think about it. This function right here, we can identify as phi sub fg of x. Right? This equation that I just wrote will show you that fg of x minus fg of a divided by x minus a is equal to my just defined fg of x. So that means that the thing I just put a curly bracket under in the big square brackets, that function is a potential difference quotient function for the product of the functions. Does it satisfy the necessary requirements for the product of f and g to be differentiable? Does it satisfy the equation? It satisfies the equation, right? Surely it satisfies the equation. That was just the step above. So we've got number 2. Is it continuous? Is this continuous at A? What do you guys think? Can you guys tell me why this is continuous? What do you guys think? Is it continuous at x equals a? What are we looking at? F of a is a constant. Phi g is itself continuous by the theorem of Caratheodory, right? Because it's the quotient function for g, which is by assumption continuous. Likewise for phi f, continuous function. G of a is a constant. Continuous function times constant plus continuous function times constant plus continuous function times x minus a. Guess what? Altogether, a continuous function. Therefore, this thing is yes continuous at x equals to a. And from the proof of the theorem of Caratheodory, not only do we find that the product of f and g is differentiable, we find that the derivative of f times g is exactly the limit of the difference quotient at x equals to a. What's that give us? What is the limit as x goes to a of this thing I just defined, phi f g of x? What happens when you take the limit as x goes to a here? What's the limit of the phi sub g as x goes to a? That's g prime of a, right? So we get f of a times g prime of a plus the limit of this piece here, f prime of a times g of a. How about that last piece, the product of the phis? What happens as x goes to a there? X minus a goes to 0, so you're left with like f prime of a times g prime of a times 0, which is just 0. So lo and behold, here you go. This is the product rule. Now, the derivation I just showed you guys is certainly not the standard derivation. Like usually people teach this a different way. They work directly with the difference quotient. They do this really weird adding 0 trick, and things work out. Maybe we'll do that another day. All right? But I would like to point out to you that the derivation I just showed you did not involve adding 0. All I did was multiply the approximating formulas for f and for g and worked out the natural rule. It's a straightforward calculation, actually. Which is why the theorem of Caratheodory. Now, the theorem of Caratheodory, it does come with a cost, right? There's an abstraction here that we're making that probably is making you guys uncomfortable. But if you saw what it's replacing, you'd realize that it's actually a good thing. Anyway, let's go on. So example 1. So I'm going to, and I need to kind of shift gears here a bit and talk about notation for a second. So notation, we are going to trade, for the most part, f prime of a for df dx at a, if you like, right? And so generally speaking, we're going to use d dx of f of x equals to df dx. That's like the notation we're going to use to express differentiation. This is the so-called operator notation. So we think of the basic idea here is you've got a function, you feed it to the operator d dx, all right? And out pops what? df dx, which you could also abbreviate, of course, as f prime. It's a new function. So our goal going forward is to find how the derivative operator works on all of our basic functions. And in fact, we've done a lot of the work in the last couple weeks already, right? I mean, on your test alone, you worked out the rule for differentiation for like 4 or 5 different particular functions, right? And but like one of the things I should do is immediately translate theorem 1 into this notation, right? So like one of the things we have is d dx of f plus g is equal to df dx plus dg dx. So this is true. d dx of cf is equal to c df dx. This is also true. d dx of the product of f and g is equal to df dx times g plus f times dg dx. So these are important rules of differentiation. This is, of course, not complete. It'll take me at least a week to complete our discussion here as we're learning the laws of differentiation together, right? So let's just start working on them. Example 1. What would d dx of x be equal to? So at the moment, the only thing we know is the difference quotient, right? So that's defined to be the limit as h goes to 0 of what? We got what? Limit as h goes to 0 of? Let me write it symbolically since you guys are not jumping off your seats to tell me what to do. So we got limit as h goes to 0 of f of x plus h minus f of x divided by h, right? But in this context, f of x is equal to what? Just what? What's my f? No. F right here. Yeah, just x. F of x equals to x. All right, so to calculate this derivative, calculate the limit as x goes to 0 of x plus h minus x over h. This is an easy one, right? So that's just h over h, also known as 1, right? Well, that's kind of cool. d dx of x, also denoted as dx over dx, is equal to 1. You can conceptualize this as like the dx's canceling, right? As if they're a fraction, all right? Now for us, they're not a fraction, right? It's a notation for a specific limiting process. But there is much to be said of this analogy of it being like a fraction. Newton thought of them actually as fractions of things called fluxions. And Leibniz as well. All of the early founders of calculus thought of differentials, derivatives, as the ratio of infinitesimals. That can be made rigorous through something called non-standard analysis, but it comes at the cost of far greater abstraction than I've already put on you today. And so I wouldn't do that to you. Next up, how about x squared? d dx of x squared, how's that go? We've got the limit as h goes to 0 of x plus h quantity squared minus x squared divided by h, right? So what are we looking at? Limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared divided by h. Do the algebra. You got yourself a limit as h goes to 0 of 2x plus h. The x squareds be canceling, the h's reduce. You get this. It works out to 2x. So what do we learn? d dx of x squared is equal to 2x. Now some of you are like, finally. Because you remember this from high school, right? This is easier than completing the square, isn't it? Lots of you know this, but don't know completing the square, I think. I certainly knew this before I knew how to complete the square. All right. So guys, can you tell me how to derive this from that? Do we need to do this limiting calculation, or was there another way? Think about this. We could have taken the following tact. I'm going to erase this upper purple bit. So another way you could understand example 2, right? Another way you could understand example 2 is the following. So another way we could have gone at it, if I'm calculating d dx of x squared, right? That's really d dx of x times x, right? So think of f of x equals to x, and think of g of x equals to x, right? Apply the product rule. What's the product rule look like here? It looks like x times dx dx. Oh, my bad. Let me keep with my product rule. It looks like dx dx times x plus x times dx dx. But what's dx dx? Well, from example 1, dx dx is 1. So we're looking at x plus x, also known as 2x. That's kind of neat. So you mean to tell me that I don't have to use the limit if I can see how to use the law? I mean, that's part of the reason I just went to the trouble there for you guys of proving the product rule at the start of everything. See, because now we can use the product rule to bootstrap our way up to all kinds of other derivatives, right? Like, let's see what it can do. How about x cubed? Any ideas? How can we differentiate x cubed? I'm feeling guilty for not proving law number 2 here, so let me pause to prove number 2. I'm not going to use Caratheodory this time. I'm going to use the more basic, kind of boring viewpoint. So f prime of a is the limit as x goes to a of f of x minus f of a over x minus a. Suppose this exists, right? You know, I probably should put the suppose first. All right, so I don't know. Here, this symbol means suppose. So suppose. Then consider the limit as x goes to a of cf of x minus cf of a. How does that work? Well, that is the limit as x goes to a of a constant times f of x minus f of a, by definition of scalar multiplication of a function. Is there a question? Okay. So we pull the constant out, and we got limit as x goes to a of f of x minus f of a over x minus a, which is what? That's the derivative, right? So what do we got? This is c times f prime of a. So there you go. This proves that if the function's differentiable, then a constant times the function is also differentiable. And more to the point, we have the following rule of differentiation. d dx of a constant times f is simply a constant times df dx. Hooray! All right. Let's see here. Example 4. Example 4. What's the derivative of 1? Well, check it out. This is the derivative of 1 times 1, which is what? The derivative of 1 times 1 plus 1 times the derivative of 1, which is what? 2 times the derivative of 1. What does this mean about the derivative of 1? If this is equal to that, that tells me d dx of 1 equals 2? Subtract d dx of 1 from this equation on both sides. You get d dx of 1 equals to 0, right? If something is equal to twice itself, it's equal to 0. If we're working over the real numbers anyway. So if the derivative of 1 is 0, how about the derivative of a constant? What's d dx of a constant? Well, that's the d dx of a constant times 1, right? So I can pull the constant out, and I have d dx of 1, which is the constant times 0, which is equal to 0. So, hooray! Now we know that the derivative of a constant is equal to 0. Yay! All right. I'm done shooting these fish in a barrel. Let us go back to x cubed. How should we do that one? What do you guys think? How should we look at x cubed? What is x cubed? So example 6 here, d dx of x cubed is, well, we could look at it this way, right? That's d dx of x times x squared, isn't it? But we already know how to differentiate x squared. And so what we got is dx times x squared plus x times ddx of x squared by the product rule. But what is that? That is 1 times x squared plus x times 2x. Also known as x squared plus 2x squared, which gives us what? 3x squared. Excellent. So there's the derivative of x cubed, 3x squared. Yep.
How did you get it to be 2x squared? Like, after like you do the x times x squared, you get dx times x squared plus x dx x squared.
This is the product rule. With f of x equals to x with g of x equals to x squared. I use the product rule.
Is that the same as the exponent rule?
No, that you're thinking power rule. Yeah, we don't know that yet. Let's learn it. Theorem. ddx of x to the n is equal to n times x to the n minus 1 for n in the natural numbers. So I'm going to show you guys a proof of this today, which involves something called induction. Do you guys know what induction is? So induction has important application to computer science. It's basically the same idea as recursion. Recursion is based on some sort of description of something that one step leads to the next, all right? So proof by mathematical induction goes like this. If you can prove a proposition is true for 1, and then if you can prove that assuming it's true for n implies that it's true for n plus 1, if that's the case, then it means it's true for all positive integers. So my claim, my induction claim is this formula. Is this true for n equals to 1 to start with? So is it true for n equals to 1? Well, what's ddx of x to the 1? We got what? Is it 1 times x to the 1 minus 1? What is 1 times x to the 1 minus 1? 1 times x to the 0. What's x to the 0? It's 1. So is that true? Is ddx of 1 equal to 1? Is ddx of x equal to 1? It is. That was our first example. Hooray. Okay, so the base step is done. So now let us suppose inductively that ddx of x to the n is equal to n times x to the n minus 1. So we're assuming that is true, right? We need to show that the rule is true for n plus 1. So let us consider ddx of x to the n plus 1. That is, in fact, the derivative of what? It is the derivative of, well, x to the n plus 1 is nothing more than x times x to the n, is it not? X times x to the n. In fact, that is actually how we define x to the power n. The definition of x to the power n is, in fact, made recursively. You probably haven't thought about this, but that is the case. Right? You just accepted like x to the n as a thing, right? Well, if I can do 2, I can do 3, I can do 4, why can't I do n, right? And if that's the case, well, now we've got a product of functions. But we proved the product rule. So product rule, we got ourselves dx times x to the n plus x times ddx of x to the n. So you guys tell me then, what can I do? I'm assuming inductively that the power rule is true for n, right? So the second derivative I wrote of x to the n, we know what it's equal to. By assumption, it's equal to n times x to the n minus 1. All right? So what? So this dx dx is what? It's 1, right? So we've got x to the n plus x times n x to the n minus 1. But check it out. That is x to the n plus n times x to... What's x times x to the n minus 1? X times x to the n minus 1 is what? No one's going to help me. What should I put here? You guys are all completely lost or completely bored, one or the other. maybe both. I don't know. What power should I put here? Do the algebra here. What happens? X times x to the n minus 1.
Shouldn't it depend on what n is?
Yeah? Oh yeah, definitely. Let me write it up here on its lonesome. What is x times x to the n minus 1 equal to?
2 times n minus 1, or x to the 2n minus 1. 2n minus 2.
X to the 1 times x to the n minus 1. Let's write it like that. What do we got? X to the n, right, because that's x to the 1 plus n minus 1, also known as x to the n. So this is x to the n down here. So what are we looking at? We're looking at n plus 1, in fact, times x to the n. But notice x to the n can be written as n plus 1 minus 1. So what this shows is that the derivative of x to the n plus 1 is, in fact, n plus 1 times x to the n plus 1 minus 1. That is exactly the induction claim, not for n, but for n plus 1. Therefore, by proof by mathematical induction, the power rule holds for all natural numbers n. So there you go. So you got, yeah, you're right. I mean, that's the power rule. So like, let's just rattle off a few. What's d dx of x cubed? It's equal to 3x squared. What's d dx of x to the 10th? 10x to the 9. What is d dx of x to the power pi? You're like, I don't know. You said n was a natural number. Pi is not a natural number. How dare you, sir? You haven't proved that. No, you guys don't say that. But it is true, in fact, that it's still true even if n is not a natural number. It's pi times x to the pi minus 1. One of the things we worked out before test 1 is that the derivative of the square root of x is in fact equal to 1 over twice the square root of x. We worked out that d dx of the cube root of x was equal to, in fact, 1 over 3 times the cube root of x squared. These are things we worked out. Check out what actually is going on here. So this is actually, let me write up in red here. So we've got d dx of x to the 1/2 is equal to 1/2 x to the 1/2 minus 1, which is, what's 1/2 minus 1? Minus 1/2. That's the power rule for n equals to 1/2. This one, d dx of x to the 1/3 power, 1/3 x to the, what's this? This is actually x to the minus 2/3. See, so yeah, the power rule actually holds for all real powers. The proof I gave you today only works for positive integers, all right? So we'd like to extend the proof past this as we go on, but you know, one thing at a time, so. Anyway, I hope that gets the ball rolling. Sorry if today was more formal than you like, but this will happen on occasion.